All right. Good morning. To me, feels like a very long time ago when we started this lecture. The first course was, or the first 2 hours we had were about principal component analysis, which are used both for visualizing high-dimensional data and as pre-processing if we need a lower dimensional representation. And well, it's maybe fitting that today we again look at the same topic, but of course looking at nonlinear, more advanced methods. Now, dimension reduction, it's always, why? Why? Because it's always a good idea to look at your data. Well, before you get distracted, I move this away. So when you get a data set, I think I've not seen a single data set in my life in which there were not any kind of artifacts hidden. So something that should not have happened, but that did happen. And you can create a nice automated pipeline, and in the end, the thing will fall on your feet because you've overlooked the artifact. And when I talk about data set, I don't mean highly manicured data sets which you find maybe for some not data sets which have been used in hundreds of papers, but if you get real-world data from some lab and you want to do something with it. Now, one reason I like computer vision is because I can actually look at my high-dimensional observations. So an image is an observation with more than 1 million, usually, coefficients. And luckily, we have a magnificent sensor, the eye, and importantly, the required processing power for that lets us make sense of these high-dimensional observations. Now, if you're not so lucky to work with images, sometimes your features or your measurements still have some correlation. A typical example would be spectra. So if you measure spectra over so many wavelengths, then the spectrum usually does not look like white noise, if there's really signal in it, but there is some kind of correlation across the channels. And well, we're used to plotting spectra, as a function of wavelength. If you're not a physicist and if it's not a spectrum that you're looking at, then this would be called a parallel coordinate plot. But if the ordering of your features happens to have no meaning, then instead of a nice spectrum, you get, one measurement per channel, and they are uncorrelated. I can connect them by lines, but it will just look like white noise. Yeah? So let's say this is a parallel coordinate plot of my first observation, and then I get a parallel coordinate plot of my second observation and of my third one, and it's difficult to make sense of that. And this is why we need more advanced methods for looking at high-dimensional data. Now, the first thing to do would always be PCA in any case, because we understand well what it does. It's cheap, or you can compute it approximately. That's even cheaper, and that's the first thing to do in any case. But sometimes linear is not enough, and then we need more complicated methods. Here's a glimpse at some methods in terms of a few data sets. So we have here in the first row the so-called COIL 20 data set, which I think is generated as follows. 20 distinct objects have been put on a turning table, and then a camera has looked at them, and then the object has turned around 360 degrees. And because the first image is the same as the last image, you know that even though the observations are high-dimensional, they should somehow form a closed loop. And now here, for these 20 distinct objects, the colors are shown in these two-dimensional approximations of the high-dimensional data, but the colors were not used in generating or in finding the coordinates for each position. Well, and then you find that some of the more advanced methods, they nicely highlight these coils, whereas, for example, PCA here, it does, not terribly bad, but also not fantastic. Or the second data set, MNIST, that's the most widely used data set at least in simple machine learning tasks. So these are tiny images of digits We have 28 by 28 pixels, and then we have some digit, and 28 times 28, this gives you a 768-dimensional feature vector. So each observation, each digit has 768 dimensions, and the task is to figure out, well, which digit is it? This was one of the early applications of pattern recognition for automated mail sorting and such. Yeah? So now we have 10 possible digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And again, the nature of the digit, or which one it is, this information was not used, but it is color-coded in these plots. And again, you see PCA. I don't know which color is which digit now. It also doesn't matter. You see that if we project linearly onto a two-dimensional, onto the best two-dimensional substrate, the colors are somehow clustered, but we don't really see, the individual digits coming out. And then if you use one of the fancy methods, we get, amazing separation of the individual digits, almost too good to believe in the case of UMAP. Well, I mean, I do believe, and these are serious scientists. Yeah, it's not cheated, but it's astoundingly good, I have to say. Yeah? And now here you see for more data sets, fashion MNIST. These are tiny images of sports, sneakers, T-shirts, etc. That's meant to be a drop-in replacement for MNIST. Same tiny size of images, but more complicated content. Here probably this method, which is pronounced TISNI, I would guess is the winner on Fashion MNIST, whereas UMAP is probably the winner on MNIST. And then we have word vectors also, which were too many to use for one of the methods listed here. Okay, so again, PCA is the first thing you should try, but sometimes you're lucky and your visualization method will bring out the structure in your data. However, these fancy methods, they do have adjustable parameters. And in the case of TISNI and UMAP, these parameters here have been tuned appropriately. So with poor choice of parameters, you won't get plots that are as nice. Whereas for PCA, all that you have to choose is, sometimes a scaling of your feature axis, if that's not dictated by nature. So do I measure, if I have length and weight, do I measure it in kilograms and kilometers or in kilograms versus meters? This will give me different principal components. So for PCA, you have to sometimes choose the scaling of features, and in any case, you have to choose how many axes. In this case, it was just 2 that was being used. For the more advanced methods, for better or for worse, they have many more parameters. So let's look at some of these more advanced methods. I want to start with a plot explaining in principle what can go right and what can go wrong. So let's say we have high-dimensional data, where in this case high-dimensional means 2-dimensional, and we want to project it into a low-dimensional space. I want to get a 1-dimensional approximation to this data. Now, if I do a PCA, let's say I want to figure out one principal component. I find the direction of maximum variance, which in this case is the horizontal one. This will give me my first principal component. And and then the data, as you remember from PCA, it gets projected onto this axis. And unfortunately, things which on this manifold that I imply here, points which are far away on the manifold, can end up very close by in this low-dimensional projection. So that's an example of a method which would be too stiff. And the effect is that faraway points get mapped to nearby locations. then I want to give an example of something which I would call is just right. If I found this as a low-dimensional axis, I would say this is just right. Summarizes the manifold. Okay, I'm not using manifold in the technical mathematical term here, just qualitatively. Yeah? So this surface on which the points truly lie. And well, if there's too stiff, if there's just right, let's look at the other end of the spectrum, a dimension reduction method which is too flexible. And so on and so on. You get the idea. It nicely, strings all these observations like pearls on a necklace. And here I've been friendly, and I've curved this necklace, but I've not really have it self-intersect. But in principle, it can also self-intersect. Yeah? So here at the end, I'm being a bit meaner. All right, this kind of method here would be too flexible. And what happens with too flexible is that sometimes points which are close by get mapped to relatively far away locations. So let's say consider, for example, these 2 points here. These are close in the high dimensional space. But as I now put them on the necklace, and I, of course, when I make now my low dimensional plot, I will say this is my axis, and I will distribute the points on the axis in the order in which I have visited them. But what happens here to these 2 points is that, okay, let me call one of them, I'm calling this one A, and I'm calling this one B. So they're really close by, but on this necklace, A is here, and B is there, and 2 other points are somehow in between, because my necklace, on the way from A to B, it makes this extra loop, it makes this extra excursion. Okay, so what happens with a method that's too flexible is that nearby points can get mapped to faraway locations, or to distal, that's a more technical term, to distal locations. So you see that there is this trade-off, which I have here called stiffness. Sometimes it also makes sense to have separate parameters for things that you want to ignore and things that you are willing to ignore for the sake of better unrolling. Yeah, so to my mind here, this green curve summarizing the manifold is perfect, because the deviations from this green curve, to me, they look just like noise. So to me, it doesn't look like there's meaningful structure. So this is actually this is information which I am happy to ignore. So here, let's say I want to ignore what I here call noise on very short scale. And now clearly, my green summary of the data it does not do some of the longer distances justice. So for example, the points which are here and the points which are there, in the high-dimensional space, they are not so far from each other, but in my low-dimensional plot of all my points, in my low-dimensional plot of all these points, they end up very far apart from each other. Now, this is bad, but there is some price we do have to pay when we want to reduce dimensionality. So this is a price that I'm willing or have to be willing to pay. And so these longer distances here, these are, I don't want to ignore them, but I am willing to ignore some violations of long distances. And usually, you know, this, what I want to ignore, this usually entails some parameter θ1 and the threshold beyond which I'm willing to ignore some longer distances. This also entails some parameter θ2. And depending on how you choose these parameters, you can get very different results. Now, everything I'm saying here is very qualitative, but the fact is that all of these more advanced methods, they make these choices either explicitly, so you have to supply the parameter when you call the routine, or implicitly somehow, you know, built into the thing, but still there. It's just that it's been hard-coded somehow. And even in those cases, changing those parameters or changing those choices would still impact the result that you get. All right. By the way, you know, a very famous example of dimension reduction is, of course, the drawing of maps. I'm looking for this picture here. So when we draw maps of countries or so, we have this problem. So our input is three-dimensional, or, well, it lives on the surface of a sphere, and we want to get something two-dimensional out because our paper is two-dimensional. And here you see, you know, some of the fundamental trade-offs that can be made. I can either try and preserve all distances, and then I get the thing on the right. And in this kind of picture, Germany and New Zealand would be superimposed. Or I get that kind of picture, which is, of course, much closer to, well, the maps that we have chosen to use in the real world. But, you know, what does it mean? On the sphere, actually, so this point A and this point B, on the sphere, they're adjacent. But we have, you know, we have cut up this sphere, and we have here been willing to actually embed them at a very large distance. And, you know, it's wrong, but it is the price we have to pay if we want to reduce dimensionality of a manifold that fundamentally cannot be embedded in low-dimensional space. Yeah, so another example, here I've given a friendly example on the top, data that was essentially one-dimensional. But what if my data looks like this? If my data, I'm trying to arrange it here in a square. You know, the data is essentially, well, the data is two-dimensional. Now I can still use all of my routines. It's just that they will give me crap answers. Yeah? So the too stiff one will give me this or that. You know, one of these will be the first principal component. Which I previously called just right. You know, with the same choice of parameters, it would maybe do something like that, or like that, or maybe like that. And the too flexible one, of course, would visit each and every point. Yeah? So the too flexible one would do a sort of traveling salesman thing here. And, well, the embeddings, of course, will be deficient because just fundamentally there's no way. Yeah? There's nothing we can do about it. Still, don't be discouraged. Usually, the intrinsic dimensionality of the data is much, much lower than the nominal dimensionality. The question is just, is the intrinsic dimensionality, or how much can we get if we really make two-dimensional or three-dimensional projections, because this is all that us poor humans can digest. Good. So, summary of this qualitative part here. Many parameters need to be selected, at least two usually, and the success of it, or the fidelity of your low-dimensional representation, okay, that's a better word, depends on, of course, the parameters that you've chosen successful or not, and on the intrinsic dimensionality of your data. Or on the topology of the manifold on which your data lie, whether or not you can get a reasonable embedding in 2D, or how many compromises you will have to make. Good. Any questions for this qualitative part? All right. Then I want to start by talking about, so I start with 0 here, and we may get to 3, though I doubt it. Let's see. I want to talk about principal component analysis again, because some of the methods will build on this, but from a slightly different viewpoint, namely in terms of the singular value decomposition. Who has heard about singular value decomposition before? All right, thank you. All right. So remember that we have as input a matrix X, which has P by n dimensions. P is the number of measurements is the number of features that I have, and n is the number of observations that I have. And this is supposed to be capital X here because this is a matrix. And when we were looking for the first principal component, we were effectively looking for a rank 1 approximation. We were saying we are looking for our first principal component, PC1, and then I wanted, for each observation, I wanted to know how far along this principal component does it lie. So the principal component, this is the new basis in terms of the old basis, and the other thing in the PCA literature, this is sometimes called the scores. These are the coordinates in the new low-dimensional basis. So when I say my new low-dimensional basis consists of just a single principal component, it is information where on this principal component do I sit. Now, if a single principal component is not a good enough summary, then I may want to add a second principal component. So this would be PC2, and then I get the scores along the second principal component, and if I want more, I can add more. Now, let's say that I'm just using 2 here, then I can also write this here as a product of 2 matrices. And they have dimensions p times, I'm going to write not 2, but r here, and then r times n, where the rank r is at most p, but usually less than p. If it is p, then I've just rotated my data. That doesn't help very much. Good, and we know, okay, I'm going to give these names here. I'm going to call this here U, and I'm going to call this Z. And we know that the principal components, they are all orthonormal. So that means that U transpose U is the identity matrix. And the problem that we were optimizing when we were solving PCA was to say that we want to approximate our matrix X by U times Z. And we were looking for both our new basis and for the coordinates in the basis such that both U and Z, or such that the product of U and Z has rank R. So we've specified how many dimensions we're willing to invest. Usually when we make a plot, the rank R that we choose is just 2. All right, and this is the Frobenius norm squared here. This is the optimization problem that principal component analysis solves. And now I've been mentioning this singular value decomposition. And the singular value decomposition says that any matrix X can always be decomposed in this sort of style that I've used here, where S times V transpose is what I've previously called Z. More space. So this decomposition, X equals U times S times V transposed, where S is a diagonal matrix, always exists for any matrix X. And is unique if the so-called singular values in my diagonal matrix S are unique, if they're non-degenerate. All right. And then we have the property that U transpose U is a, so let's see, how about the dimensions here? I'm going to assume for now that P is no more than N. The single value decomposition also exists if the opposite is true, but I'm going to be, for concreteness, I'm going to fix this here. And then I'm going to look at the so-called reduced single value decomposition, where U is P times P, and S is P times P, and V transpose is P times N. And then this U transpose U is an identity matrix, a p-dimensional one, and V transpose V is an identity matrix, or here I can say V transpose is identity matrix, but in that case an n-dimensional one. Okay, and now we can look this optimization problem. I could also say that we want to argmin x minus some approximation to x, such that the rank of x tilde is R. And so we have these different quantities here. We have x, which is the original data. Then we have z, which is the low-dimensional representation. Or I'm going to call this the encoding here. And then we have this x tilde, which is our approximation to the high-dimensional data, to the original data. And I'm going to call this here the decoding of z. Okay, so how do I encode? I can obtain, if you look at this equation here, then you can see that I can obtain z by multiplying from the left with U transpose, because U transpose U times Z, yeah, is Z, because U transpose U is the identity matrix. All right, so Z equals U transpose X. And then the decoding, X tilde, I obtain by multiplying U with a Z. So what we can say is that our encoding in PCA is a linear operation, and my decoding is also a linear operation. All right, now that was a big introduction to say, well, how can we go nonlinear? And this is where I want to talk about autoencoders. So in PCA, encoding and decoding were linear, And in autoencoders, encoding and decoding are done by a neural network. Yeah? And neural networks, the ones of interest to us, are always nonlinear. Encoding and decoding are implemented by nonlinear neural networks. And you often see a sort of this kind of sketch here, where we have a high-dimensional. So what does this mean? It means that we have a high-dimensional observation x, which I can represent, as a vector. So this would be p times 1. And then here we have our encoding neural network, which gives me a, this time x was just a vector, yeah, because I showed a single observation here. This produces a more compact representation, which has dimensions only r times 1. This is also sometimes called the latent variable. And then we have a decoding neural network, which produces a vector x tilde, which again has dimensions p by 1 and is an approximation to my original vector. Okay, and this encoding neural network can be anything you want, 100 layers, residual or not, anything you want. And then we can set up a training process where we say, my encoding neural network has parameters. I'm going to call them theta enc. Oh, this is too small for you to read. Never mind. Theta dec. So we're going to minimize the following. We will look at some loss function. It could be, for example, just sum of squared errors. And then for all observations I in our training set, we're going to try and minimize the loss or this dissimilarity between our original observation xi and our approximation xi tilde. And this approximation is obtained as follows. First, we encode xi given the parameters of the theta, given the parameters of this encoding neural network. And for a state-of-the-art neural network, this theta enc will be 1,000,000 parameters. And this here will be our approximation zi given xi and given the parameters of the neural network. And now this result we will decode, or we put into our decoding neural network. And the decoding neural network again has 1,000,000 parameters. Theta dec decode. All right, and this is now minimized over the parameters of the encoder and the parameters of the decoder. And this is how we train an autoencoder. And so what are the parameters that we have to choose? As always in networks, we have to choose the loss function, we have to choose the architecture, we have to choose our initialization scheme, and so on. So there are many choices, but we also have a very powerful nonlinear method. And I have to say I like it. So yes, there are all these parameters, particularly which architecture do we choose, but we don't have to, I mentioned earlier these parameters of the different scales. The scale, so the noise that we want to ignore, and the distances that we are willing to ignore. And somehow I don't need to make those two crucial choices by hand. And I think that's a strong point of these autoencoding neural networks. All right, so I have a picture here. This is again for MNIST. Now, the picture is from a paper that tried to sell t-SNE, so the method on the right-hand side. So, yes, t-SNE looks best here. I haven't tried this myself. How much better this autoencoding result can be made, but I would suspect that, yes, it is possible to do better with autoencoders. For example, I think it could be quite helpful if we want to get something that's a little bit sparser here, to add something like an entropy prior in this space, which again can be computed in terms of neural network that says I don't want these clouds to be so diffuse while still having some spread. I would actually be quite interested to see how well that works if somebody wanted to try that. All right, that's autoencoder. Any questions for autoencoders? Yeah.
Two questions. So in that graph, the second picture,
Yeah.
Does an autoencoder encoding your data in 2 dimensions, right?
Yes, that was the 2-dimensional one. Mm-hmm. Yeah. So here we have to choose this bottleneck here, and so we give the neural network P inputs, and then we create an architecture with R outputs. And this choice R is ours. And here it was 2. Yeah.
Do you usually do like weight sharing between the encoder and the decoder?
So for sure, there are cases where we do. So in Word, Manuel, the question was weight sharing. In Word to Vec, for example, I think it's exact weight sharing that's being used. But in arbitrary networks, not as far as I know.
So I'm not sure what the virtual people do exactly. I guess in the first generation of autoencoder, basically, you often have this weight sharing, but then people say, screw it, my GPU is big enough, and you no longer do weight sharing.
Yeah, it's an excellent question, yeah, because here we used, so the question comes from this, yeah. So here in the encoding and the decoding step, we use the same matrix, just transposed. But the thing is, if we use a neural network, with rectifying linear units, if we pass information in the one way or the other way, it doesn't do the same thing, yeah? And that's why it's not as natural to use weight sharing here.
But you are correct, the first generation definitely.
More questions? All right, then we have a break, and then comes lots more nonlinearity.